vectors, and you get an approximation. Okay? Like you did before, you said 0.33, so that's an approximation for the case of 0.34 and 0.32. So the forward computation is straightforward. First thing is you take x times w1, that's the linear combination which we introduced, that's the linear regression part of the neuron, and then you apply an activation function. I come to activation functions later, and then you do the same for the second layer. So that's the activation of layer 2. You again take the dot product and apply the activation function, and you get y. So that's what we call the forward pass. From left to right, it's called forward pass. That's if you would have ideal parameter W1 and W2, it already would do the job quite well. So the question is, how can we come up with parameters W1 and W2? So we can basically search for them using brute force. So if you now take a measure of error, so one common measure of error is the sum of squared errors. What you do is you take the actual value and you sum it up with a predicted value, and you square it, and you sum it up. And sometimes you also take then the square root, so it's RMSE, root means square of errors. That's a measure how good or how bad you are doing, given the complete data set. So for each parameter assignment, W1 and W2, you can compute the sum of squared errors, and then you plot it. So this is now, in 2D space, we have only 2 parameters. And we have here, we call it also the cost. The higher the cost, the worse we are doing. This is often called J. And you see here the 2 parameters of J is W and T. W is the vector of W1 and W2, so the parameters. And T is the training data set. The training data set stays constant. Therefore, J is only dependent on vector W. And if you plot the cost over vector W in 2D space, we get, for example, this volcano here. And what can you notice here? What type of function is this? Excuse me?
Non-convex.
Exactly. It's a non-convex function, so it has multiple local minima. A convex function has only one global minima. So finding a global minima is relatively straightforward, but finding a good local minima is not. So there are a couple of approaches. Only one works really. So I tell you why it's so complicated to do brute force. So let's consider the case that we have a value range between -1 and +1 for each parameter vector element W, and then we span a grid with a distance of 0.1 in that value range. So this looks like this. So that way we can approximate the error function. But now the problem is the dimensionality. So if we have 2 vectors, sorry, two elements, we have 411 combinations. For 3 we have nearly 10,000, and you see here it's increasing exponentially until we get, so see here, it's really a stall curve. If we have only 100 parameters to optimize over, we have more combinations than atoms in the universe. And the neural network we are training has usually between 10 and 100,000 parameters. So brute force, or more conservatively spoken, grid search is not working. Second approach is called Monte Carlo, where you randomly assign parameter values. But again, you need such a high number of samples that you are approximating the problem of grid search. So now what if we would have some magic oracle? If we take any position in that optimization space, we can all the time we can compute the cost for each position. We have the formula. That's a trivial operation. But if we now would have a magic oracle which would tell us in which direction we should update W1 and W2 in order to get a better value, a lower value for for the cost. And that's actually possible. So I'll tell you in a second how this is done. But then you can just go down the hill basically and you find a local optima. You still haven't solved the problem which local optima you want to find, but you can evaluate the function stepwise and you will always go down. You can get stuck somewhere, but you can go down. So the thing how this is done, so this is now example for a cost function, which here is dependent or which is telling you that taking the difference between the predicted value and the actual value, squaring it, taking the sum. So there are a huge variety of cost functions. That's only one example. Here are some other cost functions. So now you can basically take the formula for the forward path and you can reversely expand it. See here, let's go back, we have y hat equals a3 equals f of x3. Now what we said, we put x3 into the formula, it's a2 times w2. Now we take a2 into the formula, it's f of c2. Then we put c2 in the formula, it's x times w1. And now that's the definition of y hat. And now we put y hat into that formula here above, and we get this expression. And that's basically the cost. Okay? Given the parameters w are fixed. And now we take the first derivative of that function with respect to the partial derivative with respect to the parameter w, and intuitively we are doing nothing else than taking here the difference between the actual and the real value, and then we boost or we decrease the gradient by the weight, and this process is called back propagation. And that means here you see the partial derivative with respect to W2. I won't go into the linear algebra here, but this is basically the first derivative. And now you have the gradient for each parameter, and you compute the gradients for all the parameters, and you exactly know in which direction you have to update your current parameter vector, and then after that you will find a local optimum. Okay, so let's do a little break here and come back in 10 minutes. What's the time? Oh. Can you tell me?
11:12.
So 11:25?
Yeah, that's
okay. So let's say 11:20 Indian time and 11:25 okay.
Yeah, let's do that. Yeah. Or if you have any questions, then probably we could take that for the session, and then we can head out for a quick break, and we'll come back after that. So I was interested in the LSTM. So what, where are these applied now?
So any type of sequence data, I'm applying those on time series sensor readings, but they are mostly used in natural language processing and in audio processing. So they are, for example, there is one open source speech-to-text project which is called Deep Speech from the Mozilla Foundation. They are using a crowdsourced data set for training, which is called Common Voice. So you can, for example, maybe good idea for India, you can donate your language to the project, and then you can train a neural network. That's using RNNs, recursive neural networks. That's some variation of LSTM. Because whenever you need to remember past state, you have to add something into neural network which is capable of remembering it. Yeah?
At one point you said something about the overfit. So for the auto-encoder topology, there's this thing when if you want to reduce the overfit, you add noise to the system intentionally. So how do you do that for the auto-encoder topology?
Can you repeat the O of what?
The overfit.
The overfit. Aha. Let me answer that later. I have a complete slide deck about how to address overfitting in neural networks. Maybe I just tell you about that. Yeah? Other questions? Okay, so let's do the break and come back 11.
Yeah. So there is some P outside. I believe it's just after the corridor to the right hand side.